So the purpose of this project was to develop a load cell that can measure thrust and torque in a high electromagnetic interference filled environment. And the reason behind this is because traditional load cells use foil strain gauges, which are affected more by electromagnetic interference, and was potentially screwing with some data that NASA was collecting with electric motors. The system that we're using now is based off the fiber Bragg grating, which actually looks at the changes in wavelength of a projected light through the fiber to measure the strain.
Our initial design, which you can see here, looked a lot like a cross. The idea was that the motor would be mounted to the wide portion of the cross, and when it produced thrust, it would bend the narrower portion of the cross and induce a strain and stress in the beam, which could then be measured by the fiber Bragg gratings. What we didn't realize at first was that this actually created a strain gradient instead of uniform strain, which was really hard to measure with fiber Bragg grating sensors. To work around this problem for our final product, we decided to use a cylindrical spool design with an extremely thin neck region so that all the strain would be concentrated in that one area and would be easier to measure. Our final product was manufactured here at the UAF machine shop, where Joe Michalski did an incredible job with the extremely tight tolerances that we needed for our load cell to function correctly. Our next task was to apply the fiber optic strain gauges to the metal part, which we accomplished by using super glue, tape, and steady hands.
So here's our FOSS load cell. Now how this works is when we apply a force axially along this cylinder, we squish it, putting it in compression. Now when it's compressed, it produces a strain laterally on the surface about the circumference because of Poisson's ratio. That strain is what we're actually reading with our sensors. If you look really closely, you can see two fiber Bragg grating sensors here. So here's a test setup with the computer and the FOSS system. The fiber is connected to the FOSS, which is thereby affixed to the load cell. Here's some sample testing. We're applying 40 pounds in increments up to 80 pounds. And if you look closely at the small peak, you can see it slightly change in the reflected wavelength, particularly when we add weights onto it.
The FOSS system generates a binary file containing the reflected wavelengths at 5,000 samples per second. We're currently using MATLAB first to graph the raw data and then to isolate the wavelengths so that we can analyze the shifts under different loading conditions. Once the wavelength shifts have been determined, they can then be transformed into strain values using fiber optics equations, and these strain values can then be used to determine the applied loading.
In the future, we hope to apply this load cell in a setup like this with an actual electric motor and a flywheel and/or prop to further understand the EMI effects on load cells.